Hello, and welcome to your lecture on autoencoders. Autoencoders are our first type of unsupervised neural network. So far, everything we've done with a neural network has been to predict a certain value, thus doing supervised machine learning. Now, for reasons I'll talk about a little bit later in the lecture, some people call autoencoders semi-supervised, but in my opinion, this is the first time we're actually doing unsupervised machine learning with a neural network. In order to understand what autoencoders do, we have to review principal component analysis that we learned in the previous course. Remember, principal component analysis is a dimensionality reduction method. That means that we take a lot of information and we squish it down to represent at least most of that information in a smaller way. For principal component analysis, the way we do this is we take the axes of our data, like the x-axis and the y-axis, and we rotate them to create a new, more efficient set of variables that explain the information in our data a lot more efficiently. For example, in principal component analysis, the first principal component is going to explain the most variation, the second most, the third most, and so on and so forth. This allows us to create a cutoff point where we only take the first 5, 10, or n principal component. Because principal component analysis creates these more efficient variables, we're able to represent most of the information from our original data in a smaller number of variables, thus reducing the dimensions of our data. You can think of principal component analysis as like a lossy compression. We're taking a large amount of data and we're compressing it, and we're losing a little information along the way, but not too much. On the screen, you can see what are called eigenfaces. Eigenfaces are the result of applying principal component analysis to all the pixels in the image of a face. On the left-hand side, you can see the original images, and on the right-hand side, you can see the reconstructed images, where we've only kept 100 out of about 1,000 principal components. And then on the very right, you can see where we've only kept 10 principal components. This helps us visualize principal component analysis as a lossy compression. We're taking the photos and we're compressing them, and while we're retaining a lot of the original information, we are losing a little bit. You can see that the fewer principal components we keep, the more information we lose, but the more compression we have because the images are represented with far fewer variables. Now, principal component analysis is linear. This is because all of the principal components that are created by PCA are linear combinations of the original variables. Remember, a linear combination is just where we take a bunch of weights, multiply them by some values, and then sum them all up. And that's exactly how all of your principal components are calculated. PCA uses something called eigendecomposition to figure out what weights we should use, then multiply them by our original variables to get out all of our principal components. But what if we didn't want the relationship between our predictors and our compressed features to be linear? Well, that's exactly what autoencoders allow us to do. Autoencoders are a type of neural network architecture that basically does a nonlinear principal component analysis. The structure of autoencoders sort of looks like a butterfly because the input and the output of our network are exactly the same. Essentially, what we want to happen is we want to be able to put our data through this neural network and then have it come out the other side almost unchanged. And you might think, well, that's really boring. I could just have a single layer neural network and return the input unchanged, and that would just fulfill everything you said. But the beauty of an autoencoder is that we're not just returning our values unchanged, rather, we're forcing the data to go through a more simple representation, shown here in the middle, which basically compresses the data, and then we have to be able to uncompress it. Thus, we're trying to find a compression that allows us to have the input and output be as similar as possible while still doing that compression. The autoencoder is made up of two different parts. First is the encoder. The job of the encoder is to actually compress all of our information. So we take it from an input layer that is quite large to a middle layer that is quite small, thus compressing the information. The encoder's job is to learn this function f that takes our original variables x and turns them into their compressed version h. The other half of our autoencoder is the decoder. The job of the decoder is to take our compressed representation of the data and uncompress it. Essentially, it's learning this function g that takes our compressed version of the data and tries to recreate the original data. So you can tell that what we're really interested in when we build an autoencoder is this middle layer. This middle layer is the compressed version of our data, which we'll call H. And we might want this because we want to run a neural network on a more compressed version of our data. When learning, the neural network is using a loss function that compares the original variables that we put into the model with the compressed and then uncompressed version, which is the output of our model. Our loss function measures how close these two things are, and a perfect model would actually return the original variables because it learned perfectly how to compress and then uncompress our data. And this is why we refer to autoencoders as doing nonlinear PCA. If we built a very simple autoencoder where the encoder was linear, meaning that the compressed data was just linear combinations of the original data, and we use MSE as our loss function, autoencoders would basically approximate PCA. But of course, as I mentioned, we don't have to have a linear encoder. We can add multiple layers and nonlinear activation functions in order to add some nonlinearity into our encoder. So basically, autoencoders do a similar process to principal component analysis, but they have a lot more flexibility with how they do it. Now, I mentioned before that autoencoders typically have this butterfly shape where the middle layer of the autoencoder, aka the compressed data, has lower dimensionality compared to the input and the output. This is so that the autoencoder is forced to represent the data in a smaller fashion before uncompressing it. These types of autoencoders are called undercomplete autoencoders because the middle layer is a lot smaller than the input and the output layer. Again, the benefit here is that it forces that compression because it has to take a large amount of data and represent it with a small number of nodes in the middle of the network. However, autoencoders can also have hidden layers that are larger in dimension than the input and output. These types of autoencoders are called overcomplete autoencoders. So again, when the hidden layer is smaller than the input and the output, that's an undercomplete autoencoder. And when it's larger than the input and output, it's an overcomplete autoencoder. But you might be asking, well, why would I ever do that? Because the whole point of the autoencoder is to do compression. Well, that is still the goal of an overcomplete autoencoder. However, when we use an overcomplete autoencoder, we're also going to need to add something else that forces this hidden layer to be sparse. Sparse just means that a lot of these nodes should be forced to be 0. Having an overcomplete hidden layer allows the encoder to have a little bit more flexibility with how it's representing that compressed data. However, when we apply something like a penalty that encourages sparsity, it means that we're still going to have a low dimensionality compression. One way to encourage this sparsity is with something we're really familiar with, a penalty. For instance, when we are training our network, we can take our original loss function and add a penalty on the compressed middle layer. This basically penalizes when the nodes have values that are far away from 0, thus encouraging the network to have as many of these as possible at 0. Instead of penalizing just the values of that hidden layer, we can also penalize the derivatives. A penalty on the derivative basically forces our autoencoder to learn a function that doesn't change very much when the inputs change a little bit. Another way we can regularize our autoencoders, in addition to putting penalties on the values of the hidden layer and penalizing the derivatives, is to use something called a denoising autoencoder. A denoising autoencoder has the same structure as a typical autoencoder. However, before we put data into the autoencoder, we add a little bit of noise to it. This might look like just adding tiny random values to each of our inputs. Then the autoencoder tries to learn the original data. So the input it's getting is a slightly noisy version of our data, but the output that we want it to learn is the original data without noise. Thus, the autoencoder is actually doing denoising. It's taking in a noisy version of the data and trying to compress and uncompress it so that the output is an unnoisy version of the data. This addition of noise means that slight perturbations in the input of our data should still result in the same unnoisy output, thus regularizing our autoencoder. And autoencoders don't just have to have typical dense feed-forward architecture in the encoder and decoder. We can also use convolutional layers. Thus, we could build a convolutional autoencoder, which takes an image, compresses it, and then uncompresses it. This, by the way, typically requires that transpose convolutional layer that we talked about when we talked about convolutional neural networks. Because, of course, we're going to use convolutional layers to compress our image, and then those transpose convolutional layers to uncompress it. And we can apply all the same concepts that we talked about with typical autoencoders to convolutional autoencoders. For example, with these MNIST digits, we could actually take them, add a little noise to the image, send those through the network, and ask it to return the unnoisy images to us. Last but not least, as promised, I want to talk to you a little bit about why some people call autoencoders semi-supervised rather than unsupervised machine learning. Because autoencoders technically do have a correct answer, right? The input would be the same as the output, so our input is also our correct answer. Some people consider this to be semi-supervised. We do have a correct answer that we're using in order to train our network. However, the answer is the input data itself, so I really consider this to be unsupervised neural networks. I just want you to be aware of the distinction because you may see them referred to as unsupervised or semi-supervised, depending on where you read about them. To review, today we learned a little bit about autoencoders, which are first unsupervised or at least semi-supervised neural network architecture. The goal of an autoencoder is to learn how to compress information and then uncompress it in a way that the input is as similar as possible to the output while still doing that compression. Autoencoders are often referred to as nonlinear PCA because they're doing a similar type of compression as a principal component analysis. However, they're not limited in their structure to be linear. We also talked about 3 different ways we can regularize our autoencoders. The first way was to put a penalty on the hidden layer in our network, thus encouraging sparsity in this compressed version of the data. Next, we talked about a different penalty where we penalize the derivative. This forces our network to learn a function where small changes in the input data don't result in large changes in the compressed version. Lastly, we talked about adding noise or creating a denoising autoencoder. This regularizes our network by adding a little bit of noise to our input data and then asking the network to actually recreate the original data without the noise. And lastly, we talked about the fact that we don't have to use simple feed-forward architectures for our encoders. We can also include things like convolutional layers, which allow us to build an autoencoder that compresses and then uncompresses an image. All right, that's all I have for you. I will see you next time.